So we will wait for 2 minutes more and then I will start. So hello everyone. So let's start the session. So I introduce myself. I'm Anjali Negi. I am currently pursuing my PhD in IIT Kanpur. So today also I will take a problem and then I will teach you the detail of the basics and then we will approach the problem. Okay. So I will share my screen here. Wait. Yes, so I will share. So I hope my voice is audible and you can see my screen. Okay, so let's start. So this is the first problem that we have. So this is from GATE 2012 chemistry question number 40. So this problem state that consider the following pairs of complexes, and we have pairs of complexes, that is 1 2 3 4 different kind of pairs, and what we have to see that the electron transfer rate will be fastest in what pair. Okay, So we have to look into the electron transfer rate between these two complexes. Okay, so what actually give us the electron transfer rate in a pair of complexes is, we have in our inorganic chemistry that we study, is the outer and inner sphere electron transfer, correct mechanism. So let's go into the basic. So here we have, yes, here, so we have outer sphere and inner sphere electron transfer. So as the name is suggesting, so we will look into both one by one, and then we will approach the problem with our concept. So these are the two mechanisms, okay, by which inorganic complexes transfer electrons. So we already have seen in our problem that we have some complex complex pair, and we need to know the electron transfer rate. So first of all, what is outer sphere mechanism? So in outer sphere mechanism, whenever an electron transfer occur between two complexes that do not undergo substitution. Okay, so what do we have to look into? That in outer sphere mechanism there is no substitution, and there will be one electron transfer occur between any two between the two complex. So no new bond are broken or formed. Whenever there is no substitution, so no bond will be broken or formed, and it will remain as it is. So it involves basically three steps. So first step is the formation of precursor complex. So whenever two complexes are present in our reaction, so I have not given you the first step, but you can imagine it will be MLX plus MLY, okay, with some charge. So this will be the first step, and in the second step they will come closer to each other such that it will form a precursor complex. So this is my precursor complex. And after the precursor complex, so this is some equilibrium step, okay, K forward will be here and K backward will be here. So Ka, sorry, this arrow is, so this must be like this now, K forward and K backward, okay, something like that for the precursor complex. And this is my precursor complex. So when I have my precursor complex, that is my two complexes are very close to each other to have a outer sphere electron transfer without breaking or substituting any bond or any ligand, okay, and this will give me, this is the electron transfer step now. So after the precursor complex is formed, we have electron transfer. So this is KET, okay. So the activation or reorganization of precursor complex, the electron transfer, and finally relaxation to successor complex. So finally what happened, there will be a successor complex where you can actually note that the electron transfer has already occurred. So you can see here A plus, only A plus charge is there, whereas here A plus 1 charge was there, okay, and here the electron has been transferred from, so here we have B plus earlier, but now we have B plus 1 charge. So it got oxidized here, correct, this metal, and this metal got reduced. So it must have got electron from this metal, correct. Now after the successor complex, now this is again very close to each other, so now they have to get separate. So there is a K dissociation. So when it do a dissociation, it will again be a complex of MLX and MLY, but with different oxidation states. So now we say that these two complexes have done electron transfer, and by following the mechanism of outer sphere electron transfer. So the rate determining step is electron transfer. So here we say that the electron transfer, this one, that the electron transfer step is the rate determining step, it is the slowest step, okay. So we have to, if we want to know what which one does the fast electron transfer and slow electron transfer, we have to look into the factors that are affecting outer sphere mechanism. Now So what should be the factors that are affecting the outer sphere mechanism? So if we look into our free energy plot, so this is my free energy. Okay, so this is my free energy with respect to reaction coordinate. So this plot is basically goes from reactant to product, and we know that we form a precursor complex in between, and there is a transition state, that is the electron transfer, and after that we get a successor complex, and finally we get a product. Okay, so these are some barriers that my reaction has to cross to reach the product. Now, the factors that are affecting the outer sphere mechanism will be, so delta G dragger will be delta G dragger T, that is energy to bring reactant together. So always remember that in outer sphere mechanism, where there is no substitution, no bond is break or formed, but the two complexes must come closer to each other to form the precursor complex. Now that energy to bring the reactant together, that is including overcoming Coulombic repulsion, that is denoted as delta G T. Delta G 0 or not is the energy needed for solvent reorganization. Also, this solvent reorganization is something which will be important in the case where my solvent is also forming some kind of hydrogen bonding with the complex, or the precursor complex is formed. Then my solvent, if it is reorienting in such that it is giving stability to my precursor complex, such that forming some kind of hydrogen bond, for example, then it is very important because that supports the formation of the precursor complex. Okay, so the energy needed for the solvent reorganization and the energy required for reorganization of bond lengthening. Now, since we know we follow the Frank-Cordon principle, so for according to that principle, we know that for electron transfer, the in between any two complexes, or so the electron transfer must follow that the, at least if it is not the bond breaking or forming, but it must follow that the bonds must be of equal length. Okay, such that energy, so reorganization of bond lengthening, compressing to make interacting orbital the same energy. So actually what it means, we will look into it. So note here is that delta G naught, that is this effect of solvent organization, is the effect of solvent. So solvent, those solvent which interact strongly with complexes, example they are doing hydrogen bonding, so will reduce the rate of electron transfer. Okay, so instead of so if my hydrogen bonding, let me see if I have given you any example here. So I have not given you any example, but you can look into this, that how this solvent is actually reducing the rate of electron transfer. Okay, so by making a precursor complex little stable, so if my precursor complex is stable, then so after my precursor complex there is a successor complex, correct? So in the this KT, where is it? So this step, if my precursor complex is more stabilized, then it might reduce the rate of this electron transfer, correct? Now let's go back. So delta Gi is the energy required for reorganization of bond. Now what does I mean by lengthening and compressing of the bond, and it follows the Frank-Condon principle, is that the metal ligand bond length changes with the change in their oxidation state, correct? That is, the complex must adjust their ml bond length before electron transfer. So if we look into the example of this Fe3O bond and this Fe2 O bond, so there will be a different bond length. Okay, so you agree, I think. So but in precursor or transition state, that is, they must have the identical bond length to have the electron transfer. So what does that mean? It means that so this is my FeO, that is having two oxidation state. This is a compression here. So the delta naught value is actually small here. But in the case of my FeO, where my Fe having 3 oxidation state, so this will be having elongation bond length and having a higher delta knot. Okay. Now in the case of my transition state or my precursor complex, what will happen that for electron transfer from here to here, they must be at a equal bond length. That is what a Frank-Condon principle states. So they comes in the transition state. This is the condition, and after that what happened, that after the electron transfer is done, that is the electron is here now. So what will happen, this will change the oxidation state from 3 to 2, correct, from 3 to 2, and this will change from 2 to plus 3. So since the table are terms now, the bond length will also get changed. So this will get elongate and this will get compressed. Okay. So the example of outer sphere electron, as we have seen above, if the electron transition is occurring from Eg to Eg, so this is another note. So if my electron transfer is happening from Eg to Eg in octahedral field, so large change in the bond length Ml has to occur in sigma type of orbital. So remember that my EG orbitals are the sigma type of orbitals. I think if you look into the orbital dx square minus y square and dz square, so these orbital have head overlapping, and these form the sigma type of orbital. So my Eg orbital are the sigma type of orbital, whereas for my other d orbital, that are my dxy, dyz, dzx, so all these are actually pi type of orbital. Okay. So the electron transfer from my Eg to Eg in my octahedral field actually is a sigma type of orbital. It occur in sigma type of orbital, and therefore the electron transfer is slow. Okay. If my electron transition is occurring from T2G to T2G in octahedral field, which is pi to pi star, so this will be fast. So T2G transfer is equal to small change in the bond length, and hence it's a fast electron transfer. So this is just a note that you can actually look into the complexes that are given to you, and you can check whether the electron transfer will be happening from Eg to Eg, T2G or T2G. Okay. So the metals of second, and this is another point, that the metal of second and third row generally undergo fast electron transfer than the first row due to better overlap of 4d and 5d orbitals. So bigger the orbitals, there will be a better overlap, and better the overlap between the orbitals of two complexes metal, then it will be fast electron transfer. Now coming to our inner sphere electron transfer. So when I say inner sphere electron transfer, it is you should know that there should be something which is linking the two complexes. So here we use the bridging ligand. So the bridging ligand is very important and significant in the case of inner sphere electron transfer. If there is no bridging ligand, then electron transfer is not happening. So first of all, reductant and oxidant that are metal or complexes share a ligand in the precursor and successor complex. So as you have seen that a successor and a precursor complex is formed between two complex when they come together. So in a precursor complex, in the case of inner sphere electron transfer, there is a bridging ligand between both the reductant and oxidant, okay, connecting both of them. So on activation, the electron is transferred between the metal, correct, and the ligand may transfer between the complex. So what does it mean? The third point mean that the ligand may transfer, that is it may lose, it may break the bond with the first metal that it was attached to before the electron transfer, and it may get transferred to the other complex metal and form a bond there. Okay. So some kind of labile group is needed always in this type of reaction. So I hope you know the meaning of labile group. So CO is my cobalt here, so ammonia 5 and Cl, and my chromium H2O 6 2 plus. Now just find out the oxidation state. So for here it is +3, for here it is +2. We have to look, so you can just write down the electronic state. So here it is in the ground state and in the oxidation state that we have. So we have here 3d6, we have here 3d4, and now both of them are in octahedral field, so we can actually just write in terms of T2G and EG. So in terms of T2G and EG, we have here we had 3d6, correct? So we have T2G 6 here, and here we have 3d4, so we can write T2G 3 and EG 1. Okay, now this is K equilibrium, and so this is the precursor complex that we have. So we have our metal here, another metal here, and this is my labile group, that is my bridging ligand, that is my chlorine, and this chlorine will do the electron transfer here, and here we have ammonia, here we have water. Now electron transfer step, as it is done, you can see that this +3 will get reduced to +2, this +2 will get oxidized and will get +3. Now since this was my precursor complex, now this is my successor complex, and now the KD, that is my dissociation, will happen such that actually there is a simultaneous hydrolysis that happens here in the case of CO ammonia. Okay, also this chlorine will get substitute and will get transferred to the chromium complex. Okay, and we have 5NH3, and now you can just write down the T2G5, the electronic state in T2G and EG form. So you can just write simply as, since it is H2O here, so it will be high spin, so T2G5, EG2, T2G3. Okay, so if the above we replace Cl by ammonia, here it is very important, then it will be following the outer sphere mechanism. So what it is saying, that if we have ammonia here in place of chlorine, that is no bridging ligand will be there, so this particular mechanism will be the outer sphere mechanism in the case of we have ammonia other than the chlorine. Okay, now again the factor that are affecting the rate of inner sphere electron transfer. So this is basically the free energy plot that we can actually just make. So you can just write down here that this is one is the reactant, here we have product, and then we have the bridging complex electron transfer, and then bridging complex dissociation. So I'm just going quickly. So formation of the bridging complex is rate determining. Okay, so here in inner sphere we have that the formation of bridging complex is rate determining. This will be depending on how inert or labile the complex are. So KET versus Ka. So electronic configuration. So here is the point that I was telling you, that the electron transfer from EG to EG is slower in comparison to T2G to T2G. So if you look into here, that this is metal, this is another metal, and we have ligand distributed like this 1 2 3 4, and this is my chlorine bridging between these two metal. Okay, yeah, so what is written, yeah, so this sigma star, that is my EG orbital of metal, interacts strongly with the bridging ligand, and the orbital symmetries of metal sigma and bridging ligand facilitate electron transfer. So yes, so massive acceleration in rate from outer to inner sphere can be achieved. So actually in comparison to to outer and inner sphere electron transfer. So always inner sphere electron transfer have a higher rate. Okay. Yes. So the reason is also written as the orbital of metal interact strongly with the bridging ligand, and these orbital symmetries of metal that are sigma antibonding and bridging ligand facilitate electron transfer. So the rate is massively accelerating in the case of inner sphere electron transfer. The last point is that this inner sphere electron transfer is very sensitive to the bridging ligand, as we have just seen. That is, it is very important to have the bridging ligand in here, and it is very sensitive to it. Okay, so this is just extra information. I think I can skip it, or I can go through it. So do you guys know what are labile and inert complexes, or you want me to go through it? Any one of you can just comment. Pushpita, Gunasli. Okay, Pushpita knows it. Gunasli, can you just comment? Otherwise, I will just skip it.
Please explain.
Okay. So yeah, quickly I will go through it. So basically, labile and inert complexes. So when we talk about complex, we can talk about their kinetically whether they are. So kinetically whether they are labile, kinetically whether they are inert. So labile is the ligand which can easily substitute, and the inert means that the ligands can easily not substitute. Just keep this in mind, and let's go one by one. That is the square planar complex that we have. So if we have a square planar complex, you can just imagine that all the ligands are in the same plane, and the other ligand, if it is attacking my metal, so it can easily attack from above or below the plane, correct? And it makes my ligand already attached to the metal more labile. So labile, so since my square planar complex is not sterically hindered, so it is available for the attack and favors the ligand substitution. Now the octahedral complex, for my octahedral complex I already have 4 ligand in the same plane, and one at above and one at below the plane. So it makes a little less labile in comparison to the square planar complex, and hence it may be labile or inert. Okay, so it depends on the electronic configuration that we have, so we will look into it later. So one can actually understand on what basis they are labile, my complexes are labile or inert, on the basis of either CFT or VBT. So CFT, as we know, is a crystal field theory, came later, but initially it was valence bond theory, which was VBT. So VBT actually simply says that the inner orbital complexes, that is D2sp3, so inner orbital complexes, that is using the inner d orbital, correct? So the hybridization was D2sp3, so they were called inert, and the outer orbital complexes that are using the d orbital, that are outer d orbital, that is the hybridization was sp3d2. So those were called labile, and the inner one were called inert. Okay, in the case of VBT. So the example were given like MnCl6, CrCn6. So Mn having the electronic configuration Mn3 plus, so 3d4, and chromium 3d3. But there were some exception to this, that is the D6, D7, D9. They were all labile, but according to VBT they were inert, correct? So this exception was explained using CFT. So CFT explained that the repulsion that the electron in the case of ligand approaching along the axis is higher in the case of filled EG orbital. So whenever there is another ligand approaching to attack, so there will be electron repulsion in the case of ligand approaching along the axis, correct? And the repulsion will be higher in the case of if it is the filled EG orbital. Hence the ML bond increases and makes it labile complex. So what does it mean? That the metal bond length will increase due to the repulsion if it is if there is a filled EG orbital, and due to this the ML bond will get elongate, and this will make it more labile, my ligand more labile. So in the case of D0, D1, D2, so always remember in the case of D0, D1, D2 we have T2G filled up to 2, correct? So this is a labile case because it is easy to attack. Now in the case of D3, it is again T2G 3. So it was called inert. Yeah. So in the case of D4, if it is high spin, it is EG1, and whenever there is a electron in filled in EG orbital, that are the sigma bonding or sigma anti-bonding orbitals, then it will have a more repulsion because it is along the axis, and will make my complex more labile, that is more prone to the attack due to the metal repulsion that will happen. And if there is no, that is the low spin complex is there, so it will be inert. Similarly, you can just predict for D5 and D6 in the similar manner. And D7, D8, D9, D10 will have a filled electron in EG orbital, and will be filled in the EG orbital, correct? So it's a labile. Yeah, it's a labile then, correct. So there are some points that are in outer sphere electron transfer mechanism. Both complexes must be kinetically inert. So whenever there is a outer sphere electron transfer mechanism, always remember that both the complexes are kinetically inert, and the electron transfer take place by tunneling or outer sphere electron transfer. So electron transfer is fast in low spin or T2G to T2G, as we have just seen, correct? And the complexes having pi acceptor ligand like Cn negative, this etc. are showing actually the fast electron transfer, and the sigma donor in comparison to the sigma donor one. Okay, now there is a cross reaction is faster than self exchange, so this you can look into. Now going, so that was for outer sphere, but for inner sphere one complex should be labile and the other should be inert, and one bridging ligand should be needed, is actually needed, and it's important. The ligand transfer may happen, and the inner sphere it may happen, okay? Yeah, it's not compulsory to happen. The inner sphere rate is greater than the outer sphere rate, this is the point. And here are some example of bridging ligand, so you can look that chlorine is there, and N3 is there, Cn negative is there, bromine, iodine. Okay, now the problem that we have in our hand. So the first option was cobalt, ammonia, chromium, OH2. So this is not a bridging ligand. Ammonia is also not a bridging ligand. Fluorine can actually act as a bridging ligand, but it's very difficult for it to act. So even if I put it in a category of inner sphere, so let's have it. Let's just write it in the category of inner sphere and move to the next. So this one, as you can just look here, this is ammonia OH2, chromium OH2, and yes, so in this case it is definitely outer sphere electron transfer. I hope you are following me, as we have just covered the detail basic. So this is the outer sphere electron transfer. We do not have a bridging ligand here, and you can also write down the whether it is inert or whether they are labile, because in outer sphere, yeah, both complexes must be kinetically inert. Okay, so this you can check whether they are kinetically inert or not, these two. So this actually follow outer sphere electron transfer. Now the other one, again it will follow the outer sphere electron transfer definitely. And the last one, where we can spot a bridging ligand, and I can just write down the electronic configuration in the form of T2G and EG, and T2G is actually T2G6 and T2G3 EG1. This is inert, this is labile. So in the case of inner sphere electron transfer, we actually have to look that one complex must be inert, other must be labile, and we have it. So this is actually following the inner sphere electron transfer. Now, since we know that the inner sphere electron transfer have a higher electron transfer rate in comparison to outer sphere, so we can neglect the other options, but we can just look into the option number A and D. So option number A had fluorine here, correct? And in the case of fluorine and iodine, which ligand will show more bridging property will be iodine. Okay, so this we can actually neglect, that the electron transfer is fastest in the case of my D. Okay, so I hope you got the solution. So for this particular problem, we have electron transfer rate will be fastest in the pair, the last one, which is showing the inner sphere electron transfer. Okay, and I will recommend you to go through NPTEL reference reaction mechanism part 2 by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. So do you guys have any doubt? So okay, Gunasali. Okay. Yeah, there is one interesting problem. I think I will just play the video here. So I will move into the next I will move into the next problem. So it's a short problem, you can look.
Hello everyone. In this video, I will be solving GATE 2019 chemistry question number 51. This question states that for a bimolecular gas-phase reaction, the pre-exponential factor is given and we have to find the standard entropy of activation at 25 degrees Celsius, and other constants value is also given in the question itself. So to solve this particular problem, we have to use the Eyring equation, which gives us the relation between reaction rate and temperature. Okay, so this equation is gives us the transition state rate denoted by KTST. So KTST is actually equal to KBT, that's the Boltzmann constant, multiplied with temperature divided by Planck's constant H, exponential to the power minus delta N Draeger plus 1 multiplied with exponential delta S Draeger upon R multiplied by exponential minus EA upon RT. So here delta N Draeger is the change in molecularity in the given reaction. Here delta N, we can also write it as the change in moles between transition state and reactant. So for example, in the given problem, we have P plus Q. So if PQ is my transition state, it gives me the product R. So here the molecularity for the transition state is 1. Molecularity number of moles is equal to 2 in the reactant side. So my delta N Draeger, the change in molecularity becomes 1 minus 2, that is minus 1. So my exponential here becomes e to the power minus 1, that is plus 1 plus 1, that is e to the power 2, correct? Also, we need to find out the we need to find out the uh, uh, S entropy term. So for that, we also know we have another equation called Arrhenius equation, which also gives us the relation between the reaction rate and temperature. It is given as K is equal to A e to the power minus EA upon RT, correct? Yeah, I will just write it here. On comparison, we get this part as equivalent to a pre-exponential factor A. So hence we can write A is equal to KBT by H e to the power 2 and exponential to the power delta S Draeger upon R. Now, once we put all the values given in our problem, that is exponential 10 to the power 13, so small k. So this is Boltzmann constant 1.38 into 10 to the power minus 23. Temperature, that is 298 Kelvin. In a Kelvin scale, we have to convert the 25 degrees Celsius. And here 6.62 into 10 to the power minus 34 This is E exponential delta S dragon upon 8.31. Once we solve this, we get delta S dragon as minus 12.57 joule per Kelvin per mole. So the answer for this is minus 12.57 joule per Kelvin per mole is my standard entropy of activation. For this particular topic of bimolecular gas phase reaction, I will highly recommend to go through the lecture Chemical Kinetics and Transition State Theory by Professor Amber Jain, Department of Chemistry, IIT, Bombay. Here is the link for the lecture. Thank you.
So if you guys have any particular topic for me to cover, I can take it in the next live session. I think 6 live session are still remaining. So or it's fine. So you guys have any doubt from today's topic that we covered? Okay. Gunasali?
Clear, ma'am.
Okay. So, okay, I think I will wrap up the session now and we will meet in the next session. In between, if you guys actually want me to cover any short topic, you can mail me. I think Gunasli have my email ID, or you can just think about the topic, yeah, and mail me later, or just can type now. If Pushpita, if any topic you want. Okay. So, yeah, thank you so much for joining. So I will end the session now. Yeah, thank you.